This video is part of the MCAT chemistry video course. Subscribe if you'd like notifications about the release of new videos, and visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we're going to go over thermal expansion and how temperature and kinetic energy are related. Thermal expansion applies to both linear and volumetric expansion. Our first equation here is for linear expansion, and this is referring to the change in length of an object as the temperature changes. And we can see here we have delta L, which is change in length, equals alpha, which is a constant that will depend on the substance, multiplied by the original length, multiplied by the change in temperature. So all you would do is figure out what's your change in temperature, multiply it by the original length and alpha, and then you'd figure out how much your length changed by. And what the equation really tells us is that we have a linear relationship. So the more your temperature changes, the more your length of your object will change as well. We can use this idea when looking at a thermometer. So there's a thermometer there. Linear expansion becomes really important whenever you think about thermometers. So on the right here, we have a thermometer. And here on this black line is where the liquid is at its starting point. And as the temperature increases, we can use this equation, which will show us how much the length of the liquid is going to change. And it's really important to note that that change is going to be linear. So if 1 degree makes that line rise by, let's say 1 millimeter, let's say that a change in 1 degree makes that go up by 1 millimeter. Then for every single degree that we go up, every time that line will rise by 1 millimeter, every time 1 degree is added to the temperature. Next, we have volumetric expansion, which is pretty much the same thing as linear expansion, but we're applying it to the volume instead. The equation is really simple, except we're using beta instead of alpha, and beta is actually just 3 times the alpha. So let's say you're working with a substance that has a certain alpha value for it. To find the beta value for that, you just multiply the alpha times 3, and then you could apply that to the volume. And then we start out with an original volume instead of an original length for that equation. And these two equations can only be applied to liquids and solids. They do not apply to gases. The temperature of a gas is directly correlated to the kinetic energy of the gas molecules. And it is shown in this equation here where we have kinetic energy is equal to 3 over 2 times Kb, which is a constant, times the temperature. So as the kinetic energy goes up, the temperature goes up, and that relationship is linear. And the kinetic energy, this would be the average kinetic energy of all the gas particles in a given gas. And conceptually, how you can think about this is imagine you have a couple cubes here that contain a bunch of gas particles, and those gas particles are moving and bouncing around everywhere. And if you were to put your hand in one of these cubes, then the energy from those gas particles bouncing around is going to be transferred into your hand, and it's going to allow you to feel some temperature. And the faster those gas particles are moving, the more energy will be transferred to your hand, so the temperature is going to be greater. It's going to feel hotter. And if you doubled the speed, you would double the temperature. Now, this gets a little bit more tricky whenever we think about what would happen if we say we only had 2 gas particles that are bouncing around. And we're going to say that the kinetic energy of cube 1 is equal to the kinetic energy of cube 2. So if you put your hand in cube 2, the energy is still going to be transferred to your hand, but it's going to happen way, way more slowly. So yes, it's not going to feel as hot initially, but over time, as that temperature gets transferred to your hand, it's eventually going to feel the same temperature as cube 1. And this is assuming that all the collisions are elastic, meaning that when the gas particles collide with your hand, they're not losing energy. So they're transferring their energy, but they're also moving at the same speed as before. So cube 1 would transfer the energy faster, so it would feel hotter initially. But ultimately, cube 1 and cube 2 are the same temperature. Cube 2, you would just need to have your hand in the cube longer in order for it to feel as hot as cube 1. So ultimately, you just need to be really confident in the idea that the average kinetic energy of all the gas particles is directly correlated with the temperature of the gas. And when we talk about temperature, we always are assuming we are using Kelvin. And Kelvin is a really nice scale because whenever the temperature in Kelvin equals 0, that means that the kinetic energy of the gas molecules is 0. And you can never get below a temperature of 0 Kelvin because your kinetic energy can never be less than 0. And to get Kelvin degrees from Celsius, all you do is you do Celsius plus 273 degrees equals the Kelvin, equals the degrees in Kelvin. So absolute 0 in Celsius would be C plus 273 equals 0. So in Celsius, that would be negative 273 degrees to be absolute 0.